To yet another video of theoretical Mindustry logic. I've seen lots of people on the logic channel try to build their own operating systems, but they never really had any groundwork to base themselves on, so I present to you the Mindustry Unix-Like system, or MULe for short. MULe, like other operating systems, will have a kernel, file system, and even system calls for user programs to use to interact with the rest of the system. The reason I'm saying we'll have is because I haven't done it yet. As you can see, the processor is empty. I'll just describe the architecture to tell you what the future of MLog real-time OSs might look like. Any modern file system has a root. I mean, any modern operating system has a file system, but this one is interesting. Like Unix, it does have a root. Every file in it has an owner, a group, but here's what sets this one apart. Because of how limited logic is, as you can see, there's only 64 memory cells, spots for values. Every file is either a memory cell or a bank with a file with a maximum size of 50 or 500 something doubles. Remember, the metadata takes up some space too. Or it's a read and execute binary, in which case there's also a processor using a memory cell as a control bus. So, for example, this processor is going to have itself bound to cell 1 and nothing else. Maybe with an instance number and processor number for longer programs that span multiple processors. However, storing everything in this file system won't make sense, even if we have special directory files with their direct names or // their name, because this is just a root file system where we mount our binaries and devices and everything else. For example, I would mount directories such as etc, var, home, and mnt to a device driver and dev. That's these 5 processors here, in this whole block. Like the one I'm... you get my point. To not contaminate the file system. Bin and dev, however, are located on the rootfs because the kernel can directly access it. You can see these cells are actually bound. Now we have a file system, we actually need system calls, and without them we won't have binaries. Because of Unix and how it normally works. Here's some system calls we must have. Open, close, read, write. Spelled that wrong. These are the ones we need to actually access the files. The stat family, stat, fstat, lstat. The mmap family, so like memory map, memory unmap, memory remap. Of course, then some other syscalls like memcopy, memory alloc, free, etc., as well as signal call. You get the idea. There's going to be a lot of system calls. But the way this should be handled is like the kernel reads them from a certain location in the process memory. So let's say right before the system information, there's the file system information might have things like UID of owner, GID of owner, the time it was added, and in this case we have the name of the file in the last one. Basically what the kernel does is it reads one of these. It reads all of these on the right, and if it finds something that's not just 0, it's gonna parse it as a name. But at some point, maybe like cell number 59, we might have a system call number, and then you could pass arguments into it, and it'll do whatever the process wants, unless it's not run by root, of course. The kernel doesn't actually know how big the file system is. Hell, doesn't even know how big its memory is. For example, you see this here. I might have marked this main memory and then marked this kernel memory, but the kernel doesn't actually know for sure. You need to actually give it some info, and it only knows 2 things for certain. This first memory cell here is going to be the type of memory used in its main memory part. So, for example, if this first memory cell, bank 1, is a bank, then this means that all of this memory is banks. It's going to treat as banks no matter what. This is for speed, actually. And the second thing it knows is that it needs to find a file called init here. Somewhere here. It doesn't matter where it actually is. It'll just search through all the files until it finds init. If it doesn't find init, it'll, of course, try look for it again and again until it actually finds it. Then, once it actually finds init, it's going to copy from it, or if it's a binary, it's going to try to use bank switching to copy itself into kernel memory, because, memory cells are smaller than memory banks. And the init cell is also going to say how long. The init cell is actually going to say, it's going to dictate how big this whole file system is. So, like, how big each cell is. 64 or 512, because this thing has 512 memory instead of 64. Right, so it might include things like how big the kernel memory actually is. Sometimes it might not actually be included, but kernel memory can just not only be this bank, it could also be this, and this bank. How it knows that is because these banks are sequentially added, and you can just write to a location here, and the kernel will know that, hey, this is my portion of memory, I'll use it. And maybe some other kinks like device mapping. For example, you might see that this sorter keyword, if I press something on it, it's gonna output to this cell, like this cell here, and then you might have a device driver listening on this cell, and then this cell as well. So it's going to copy whatever it is from cell 2 and then pass it to cell 1. That's going to cause a software interrupt, which this kernel is going to pick up. There's actually 4 processors here because syscall context handling also happens in different processors, just to increase the speed a bit. Maybe initialize any pipes between the devices, start some processes, because init says that there must be some pipes, there must be some other syscalls happening, and that's the MULe architecture. So what should actually we be avoiding? Because keep in mind that this is very close to the Unix file system, which means that there's users beyond root, right? So there's going to be maybe a main user, maybe an administrator with sudo powers. So first things first, it's that we should not put any permissions inside of these cells here, because keep in mind that these processors, this one isn't actually linked because these are all dummy processors. These processors actually are going to write to the memory cells below them, right? So if they write their UID to be 0, that's going to be an easy way to get root access and screw the system over, because you can do any syscall you like. Instead, you should store permissions somewhere in the kernel memory or in the main memory, because that's where the generated file system permissions will be, generally. Second, never trust anyone besides root. That's obvious. That's obvious for Unix-like systems. Anyone that can add binaries and config processors is also considered root. So, for example, if you have a poly going on, that poly is pretty much root. But there's not really much they're going to be able to do besides maybe import processors from other Unix systems, but that's more a question for device unit control. Second, and lastly, we're going to need to consider adding more functionality, because the only thing that's actually going to be writing to the system is this keyboard. This keyboard is going to be your only interface to the system, so you might want to have a text terminal, I don't know, so you might have a message terminal, config this here, then you write some program into it that will write here and then maybe print later. And maybe you want to add a display, maybe you want to have library powering this display, and you might want to be able to do unit logic as well, because get block is actually really powerful. And with it, you'll be able to control the entire world, really. You could control units on the other side of the map. It's just a Unix system. You can just do whatever you want with it. I'm Router, and I'll see you in the next video, where we're actually gonna try to program this thing. I'll see you later.